SwayamPrabha. Digital India. Educated India.
Okay, so we started discussing about bypass transition. What we have studied so far was wall excitation and free stream excitation with periodic vortex train. Today we are going to look at another aspect where we are going to excite a shear layer by aperiodic vortex. Well, it means just a single vortex. And how does it trigger transition to turbulence without going through creating transition Tolman Schlichting wave? That's what we call as bypass transition. So we want to do that. And these are the potential application areas where you see such a thing happening. For example, we have talked about in fluid mechanics unsteady flow separation. This is a paper, Degani et al. They wrote about it. This unsteady flow separation implies that you would have separation bubbles which will go along the surface. And they also show you enhanced skin friction and significant separation. Separation phenomena, will club them as bypass transition. Brinkman and Walker did similar studies where they tried to see how eddies or vortices form near the wall inside a turbulent boundary layer. So what you do is you look at the spanwise plane, YZ plane. Suppose the flow is in the x direction. In the YZ plane, you postulate the existence of a stream function and you solve stream function vorticity equation. And then if you see there are some streamwise vortices in the spanwise plane, that would create the bypass transition. So that is one thing. That's what we are talking about, that the transition occurs here completely differently other than what we have studied so far through linear stability theory in a quasi two-dimensional framework. So this is something that we would continue looking at, and this was also been discussed how similar such mechanisms, the model that we are discussing, this is basically a prototype model. We are just trying to see what happens to the shear layer if a single vortex goes by. This is a unit process. So that kind of unit process has been earlier been postulated by Smith and his colleagues, and Robinson in his annual review paper. They tried to find out how hairpin vortices forms inside the turbulent boundary layer. That's what we are talking about, near wall turbulence phenomena. That also comes about there. There was another group of people in UK who have studied a very interesting problem, that if you have a flat wall, you bring in a vortex, and the vortex automatically starts by itself. Why? Because we discussed it in the last class also, that if I have a wall, and let's say I have a vortex here, then because of the wall I would have a with a negative sign. So if I look at this point, what happens? We saw that induced velocity by these two gives rise to this. So this creates a kind of a slip velocity. In addition, what you can see, that this vortex exerts a force on this, and this in turn gives a force on this. As a consequence, both of them start moving. So you start with a no flow, just simply put in a vortex, a singularity, you start seeing this vortex translating. And once this vortex starts translating, that also would be something like the complementary flow, where the vortex is stationary but there is a flow inside, isn't it? So what happens is, it's kind of a similar problem that we are proposing here too. And this was investigated by Perridier, Smith, and Walker in a couple of papers in Journal of Fluid Mechanics. And the vortex was placed above a plane wall. that caused the vortex to migrate, and at the same time a thin unsteady boundary layer was formed. Right? So it will immediately start forming a boundary layer, and then this vortex will destabilize that. So it happens, it just brings in a kind of a sequence of events that all starts about by just simply keeping a single vortex in a quiescent fluid. So this is something we must understand. It's a very, very interesting phenomenon. The moment you put such a vortex in front of a shear layer, you create a kind of a primary instability. And this we have studied a lot over the last 7-8 years. In many scenarios we have studied it. The last paper is actually an experimental paper which we did a few years ago in Singapore. I will explain that work. The first paper is the where we proposed a new theory of instability based on energy. So that is also we are going to study in a great deal. And the second paper in 2005 that we are looking at here, we studied the instability of a sort of a flow over a wing, swept back wing on the leading edge. This is what is called as a leading edge contamination problem. That's what we have to talk about a great deal too. Now we have noted already that if we have a train of periodic vortices in the free stream, that creates some kind of a wave packet whose dynamics is different than those produced by monochromatic wall excitation. That monochromatic wall excitation typical example is the Schumann-Kramstad experiment that we know. And we also noted that qualitative differences do exist between free stream and wall excitation. We talked about wall and free stream modes as two different types of responses that can be created by this kind of excitation. And we also investigated the case that if I, even though I create just a free stream excitation, that by itself creates an equivalent wall excitation. This coupling mechanism was studied in great deal in last week. We recall that. And we see that there are two types of excitation. In the vibrating ribbon experiment, monochromatic Tolman-Schlichting string waves are created, which travels with a constant frequency and tends to stay very near the wall itself inside the shear layer. Then secondly, what we also notice that the free stream excitation can create both downstream as well as upstream propagating disturbances. That's what we call the downstream propagating ones are the wall modes, the upstream propagating ones are the free stream modes, right? That's what we say. Finally, we noted that in contrast to vibrating ribbon cases, the free stream excitation can create disturbance wave packets which remains within the unstable band over a longer distance and also suffer much larger growth rate. This is something that we must keep in mind. In contrast, if we look at periodic train of vortices convecting in the free stream at constant speed, we don't have to follow a constant frequency, but what we should follow in that neutral curve, we should follow c equal to constant line. And that's the reason that we get much higher growth rate, right? We said that as a consequence, the growth rate of waves will be much, much more significantly higher than what you actually generate by vibrating ribbon type of excitation. Okay, so now what is new on plate now? That's what we want to talk about. But what we noticed that for free stream excitation case, we have a band of convection speed which we actually identified. If the tunnel length is small, then this is the most lethal speed at which a vortex can go. We'll revisit that, what really happens, and we'll talk about specific mechanisms by which this kind of excitations can come about. But the most important difference that exists between wall and free stream excitation is the direction of propagation of disturbance field that we have talked. So we're emphasizing again, free stream excitation is equivalent to upstream propagation with respect to the disturbance. So with respect to an inertial frame, it still may look like going downstream, but with respect to the disturbance in the free stream, it actually moves upstream. Okay. And then if we have just simply low amplitude wall excitation, then we see that we do create those TS waves. But we also keep in mind that if the amplitude is much larger, then we can also have a bypass event, even though we are having wall excitation. So this wall mode that we are talking about is restricted to very small disturbance case. Okay. Now, when the shear layer is excited by train of vortices in the free stream, then a part of the disturbance field travels upstream in addition to this wall mode. Okay. We also noted very clearly that if we create a disturbance even inside the shear layer but at very low frequency, then we do not create any two-dimensional disturbance field. Instead, we create a three-dimensional disturbance field, which we call as the breathing mode or the Klebanov mode, right? So this is what is basically a quick summary of what we have been talking about. Now, what we are talking about, that if we just don't talk about this synthetic lab scenario where we do this vibrating ribbon business. In actual flow, what will happen? The flow itself is not uniform flow. That contains all kinds of things. You have a periodic vortices, you have an aperiodic vortices, and you know if you have a periodic vortices, then you can have an equivalent wall excitation, all kinds of things. So in the response field, what do you see? It's going to be a mixture of all kinds of potpourri of things, some two-dimensional, some three-dimensional. And what about the three-dimensional disturbances? We saw that that could be due to the very low frequency excitation, and those wavelengths could be thousands and thousands of delta star. So that may span the whole experimental facility and many times over. Okay. Now we also talked about some direct simulation ourselves, but in addition we also note that there were some direct simulation, 3D simulations were done by this group at Stanford, Wu et al., Wu, Jacob, Wu, Durbin, and Hunt, this 1999 paper. Later on, Jacob submitted his thesis under Durbin. There also they talked about this DNS of this free stream excitation, right? What kind of free stream excitation was considered? In Wu et al., it was a periodic wake like what you would see in a turbo machine. Like we talked about the stator-rotor interaction. It is that kind of thing that they talk about. Whereas in Jacobs and Durbin, they were created what is called as a free stream turbulence, they call. But please do understand that they were basically talking about those modes are called along that alpha I axis. Remember, we talked about the anti-Stokes line on the right half plane. We have alpha R positive, and on the alpha negative we have these two kinds of things. So this Jacobs and Durbin's work actually talked about some disturbances which lie along alpha I axis, and we discovered its eigenstructure, that it will not decay. It will not decay. So it's a kind of really a synthetic free stream turbulence. Many of us do not agree with this way. I mean, you can't ever excite a flow like this, that the excitation goes all the way up to infinity and it just zigzags like this. In contrast, this earlier work by Wu et al., this periodic wake was much more realistic. That kind of depicts what happens in actual turbo machine. And if you recall that Kendall's experiment that I talked to you about, where what Kendall did was created a kind of a circular cylinder rotating about this, and then it was creating vortices alternately like this, and so on and so forth. That also was a sort of a kind of a prototypical model. Whether you are talking about Kendall's experiment or Wu et al.'s free stream excitation by periodic wake, what remains in view is a kind of a qualitative picture, because we do not have any idea about the strength of these vortices, those are coming. And we also do not know what happens to the vortex. Does it go towards the downstream plate, or does it go at a constant height, or no, I mean, there are too many unknown factors, parameters. So that's what we thought when we started looking at it in late 90s, that we'll have to design an experiment which should circumvent all of these uncertainties. And that is what we'll be talking about a great deal Okay. Now, what happened was those two papers, those are written by Wu et al. And Jacobs and Durbin. They looked at some structures in a direct simulation result. What they noted is written here in green, that before transition you could see some kind of structures which were propagating upstream, and they look like a jet. So basically that's what you see in turbulent flow also, peak valley structure, and then you have sort of a stream of fluid which is going relatively faster than the other. But look at this, they were the ones first who did talk about that there are something like backward moving flow structures, and that was computed, and it was a very brilliant piece of work. However, they could not give very good explanation for it. But now that we have done that analysis ourselves, and we know what causes upstream propagating modes, those are those eigenvalues which remain on the left half plane, that can give rise to this. And this made them suggest this, that this creates in turbo machines, you do get some kind of turbulent spots, spot-like behavior, creates an elongated streak of velocity fluctuations. So you have peak and valley structure, and they are sort of distinguished by this feature of propagating upstream. And this was something totally new. Very few people understood or appreciated at that point in time. But when we did those calculations, we did understand that what it was. These were this Klebanov modes plus 2D upstream propagating modes. The upstream propagating mode, as I said, is a 2D component of the disturbance field. In addition, in turbo machine, you also see that the boundary layer heaves the whole thing. That is, of course, is the signature of Klebanov mode, right? That we have seen. So those are those three-dimensional flow field, disturbance field, but we've seen its peculiarity. It's three-dimensional, but moves along the streamwise direction. So this was a very, very queer piece of evidence. The DNS produces results for the imposed disturbance field, but it does not really give you a complete understanding what is really going on, right? That is one of the problems with computing always. You have to understand that it can give you a lot of results, but it does not give you immediately an explanation. Although there are groups of people these days, they talk about artificial neural network, which pretends to learn by itself without the person writing the program. He or she does not have to learn, but artificial neural network learns and does a lot of interesting things. I'm very skeptical about machine doing the thinking and understanding for you. But there are lots of people who are making a living out of it, so we'll not criticize them too much. I think the numbers are growing by thousands year by year. Look at, in contrast, the kind of simulations that we reported. Here we talked about that even though we are talking about pure convection with a prescribed velocity and time scale, but due to dispersion, we can actually fill up the band. That was one thing that we did. And in this work, of course, we did connect the wall mode and the free stream mode, and we shown why you get much larger growth because of this kind of a scenario, right? Okay. And that's the scenario of Kendall's experiment. Okay, and we did talk about this. We looked at the shear layer, where the extent of the domain started off somewhere from 150 to 1900. This is Reynolds number based on displacement thickness. So it was not a very long flow field, but in recent times we have actually done the simulations. Shagato has done it over much longer domains, and we find that this range actually depends on what you do. So what does it mean? It means that whatever tunnel that you are using, you are going to see the selective speed slightly differently. Because in essence, you are creating all those waves which are restricted by the size of the tunnel. So if you have a much longer tunnel, then you could create much longer length scales, right? So this is something that experimentalists also should pay attention to. It's not that without knowing the theory you can do experiments. Unfortunately, a lot of people think that way, that if you are not good in theory, you should become experimentalist, which is not the case. Whatever the instability that we have observed in all these cases were still by the tall mist-resisting wave generated packets. That was true if the perturbation is kept very small and the root of instability is not truly the bypass transition what Markovin suggested, that you don't see any TS waves. So these are still TS wave generated packets. However, if you keep on increasing the free stream turbulence intensity, which is about 1%, 1% is quite large by pure external aerodynamics application point of view. But when you look at internal flows like flow inside a combustion chamber or turbo machines, there this may be considered even moderate, right? Immediately after the combustion chamber, you could have a free stream turbulence level close to 2 to 5%. So that's quite common. And another place where external aerodynamics you could have very large free stream turbulences, what you see in wind aerodynamics. No? In civil structure, you talk about gust of wind coming. So in a storm, if you want to study, it's that kind of a scenario. So if you have FST level higher than 1%, then you bypass the TS route. Okay. It's interesting that Jacobs and Irwin made this observation, which we would not like to agree immediately. What that they say that is inertial time scale processes come into play during bypass transition, irrespective of, I mean, you are not having a TS wave, so there are additional time scale coming about. This is due to the inertial acceleration term, right? Convective acceleration term. But they confessed that their origin and nature were not known to them for sure. And they made this observation that bypass transition is stochastic in nature. And that's what they say, that give up your deterministic fluid mechanics and start dabbling in statistical fluid dynamics, and which you know that we should not subscribe to, because that's what we are going to see what happens. Now, understanding bypass transition actually suffered, because you have to do some experiments on which you can really control one parameter at a time. If you don't do it, then you see all this potpourri of effects together. Now we are pretty much conversant in actual transition scenarios. So many things can simultaneously happen. If you cannot identify the cause and effect yourself, God is not going to help you, right? So you have to do some definitive control experiments, by which only you can identify the physical mechanisms that would help you, the same way that Schuber and Skramstad's experiment established instability theory the first time. So this was a revolutionary piece of work. Here also you need some such good, well thought out experiments. And this was clearly articulated by Percy Smith. He said that if you want to identify unit processes that goes on inside a boundary layer, whether it's either transitional or turbulent, then you need to really follow the link, the causality of input with the response field. It should be in the same spirit as Schuber and Skramstad did. So what do we do is the issue. That's why we stepped in. Manojit Chattopadhyay was one of my students at Singapore, and Professor Lim was a colleague. So we all gathered around. We thought we'll design and do an experiment to do some of this. What we did try to create a bypass transition, and purposely we wanted to keep the scenario very simple. So we had to initiate something which was really a two-dimensional mechanism. Because if you are doing an experiment in a turbulent in a wind tunnel, and if you also have transition to turbulence, and you have the sidewalls, and you have the three-dimensional thing, then all those reflections, etc., is going to quire the pitch completely. And that's what we decided, that we'll have to do something very original, by which we'll keep the flow essentially two-dimensional for the disturbance flow, and then we'll see the energy spectrum. Because you see now what is happening. We are trying to create a single captive vortex that will go over, and that will create some instability mechanism that will remain two-dimensional. Too many things we tried to constrain, and that's made that design of that experiment very, very interesting. We were not very ambitious. We wanted to really look at the receptivity stage itself, how the whole thing starts off, the onset process. Okay, we used a water tunnel, and tell you what, in retrospect, when I look back, we spent only about $100 Singapore dollars in doing this experiment over 2-3 days. We just simply depended upon a dye visualization technique, and we tried to create the bypass transition by first creating a captive vortex and then making this vortex do your bid. You want it to go at a constant height, it should do it. You want to keep it strength fixed, it should do that. So all that was done, and we also wanted to control the speed of convection of this vortex. And what we know, all that we have learned so far, that it should not be a pure convection mode. If we are talking about the bypass route, then this convection speed should be different from the free stream speed. So let's go ahead and see what we can get. Now, what we are going to get is a kind, what we call as a vortex-induced instability, because that's what is happening. We are making one single vortex go by, and that destabilizes the flow. So this is quite challenging because of those parameters that you want to control. The control parameters could be the strength, the propagation speed, the height, etc. And not only that, even the sign of the vortex. You know, on order, you want to create a counterclockwise rotating vortex or clockwise rotating. How do you do it? Okay, that's what we did. We created a vortex by rotating a cylinder. You know that Robbins-Magnus effect creates a very potent coherent vortex at the center of the translating rotating cylinder. So we did that. So we said that this will do the trick, and by the rotation direction we could fix its sign. And because now your vortex is trapped inside the cylinder, you have kept the height fixed. And what we did, we also had a stepper motor to guide its motion. Sometimes even we could do it manually, so that we can control its speed of propagation. So you see, this was a very, very simple-minded experiment, but we did achieve quite a bit. And all these things were achieved. We created a captive vortex of a particular sign. We could control its speed. We could control its height. Now, you might say that, oh, you've taken a cylinder, and then the cylinder sheds vortices that may not common vortices. What happens to that? This, I will give you some reference as we go along. Earlier experiments have shown that if your surface speed is more than twice the speed of, surface speed imposed by rotation is more than twice the speed of u infinity, the oncoming flow, then the shed vortices are negligible. And then even if there are trace amount, we'll show visual experimental signature of that those strengths are orders of magnitude lower, so you don't have to worry about. So what actually we did, we used Robbins-Magnus effect to create vortex-induced instability. Now, when you think of the role played by the captive translating vortex with a finite core size, can it destabilize the shear layer? Well, people have conjectured about it, and no one else other than G.I. Taylor in 1936. He had thought about it, But what he thought was that you have this vortices going past in the free stream, and once you go in there, that will constantly excite. So it's not a question of instability that they are talking about. They are talking about a forced excitation. You have a constant stream of vortices going, and that keeps on buffeting the shear air, and that's what you see as the response. So you understand that there is a qualitative difference between what Taylor suggested, and which is actually given in the book by Monin and Yaglom. You can read that in the early pages. That scenario is entirely different than what we conceived of and we did. Okay, this was done in that recirculating water tunnel in NUS. This is the sketch of the experiment. So all you needed is basically a perspex flat plate. So flow is coming from right to left, and then this is a top view. So in the top view, this is your rotating cylinder. So you see it's rotating with capital omega, and it is also convecting. Now what it does is this is a side view, right? So this is the plate, and this is the vortex that is going at a constant height h, and the speed c is fixed by us. RPM we can change ourselves, so we have every control, and we also have a flap. You know, in all flat plate experiment that you do in tunnel, you always need to have some such flap to somehow control the flow, because although you may say that it's coming like this, it really does. You'll always have some kind of a flow angularity, etc. And to offset that and to create a perfect zero pressure gradient boundary layer, you need to have a sort of adjustable flap. So this is a usual tricks of the trade. So what you do is you have this rotating cylinder, the flow is this way, and this cylinder is moved at a different speed. So c is not equal to infinity. And how do you visualize the flow? You create some kind of dye holes, and through there we actually simply injected food dye. And what happens is, if I don't have this, those dyes show as if they go in straight line, and that establishes that the flow is perfectly two-dimensional and there is no pressure gradient. And then once you start the experiment, this dye will fluctuate. These dyes will suffer enhanced mixing, chaotic motion, all kinds of things. And this is these are some of the details of the tunnel. The test section was not very much. It's just simply 40 centimeter by 40 centimeter. We had about 1800 mm long test section made of transparent plexiglass. The flow was made to really be quiet by passing it through a series of honeycomb and screens apart from the contraction section itself. The flow velocity is actually controlled by AC motor, which drives the centrifugal pump, because it's a water tunnel. So you have to spend power through this AC motor. That is kept on the return leg. So it's basically not in the same, so it's a kind of a recirculating one. So you keep it on the return leg, and then you have all this contraction cone, you have the screens, you have the honeycomb. So the time the flow enters the test section, it's absolutely quiet. It's absolutely quiet. And the plate that we took was about 110 centimeter long. And if this is the channel, so we kept the plate vertical so that from the side we could take pictures, right?